Assalamu alaikum warahmatullahi wabarakatuh.
Welcome to the Deep Dive. Today, we're opening up a stack of sources that, well, they don't just describe historical swords.
No, they really define entire martial systems.
Exactly. We're looking at these blades not just as pieces of metal, but as highly specialized, optimized machines built for very specific combat roles.
That's really the key takeaway from all the material, isn't it? When you analyze these weapons, you start to realize the design choice, straight or curved, long or short. It tells you everything about the geopolitical environment they were born into.
So today, we're unpacking fabrication secrets, some really complex techniques.
And the core design philosophies that dictated whether a system needed, say, maximum thrusting precision like a rapier or just the brutal, simple cutting power of a dowel.
Okay, let's get into it. We're aiming to cut through the folklore to understand the fundamental engineering briefs. Our mission here is to dive deep into these sources and figure out what truly made a historical blade effective.
And a great place to start is with designs that just endured.
Let's do it.
So if we're talking about longevity and just pure functional efficiency, we have to start with the Roman gladius.
Of course.
Our sources confirm its dominance lasted for roughly 800 years. And what's fascinating isn't its elegance, but its ruthlessly practical engineering.
Right. Everyone knows it's a short sword, but the common explanation is always just, it's good for close quarters. That feels a bit too surface level for 800 years of battlefield success.
It is. It is too simple. Its success was less about just fighting next to other soldiers.
Not hitting your buddy in a shield wall.
Exactly. It was more about maximizing lethality against other soldiers who were also locked in formation. The Romans fought with their shields interlocked, creating this human wall.
A literal wall of shields, yeah.
So the gladius was specifically designed to deliver a short, controlled thrust. Aimed low, aimed quickly. The whole idea was to maximize the chance of slipping it under an enemy's shield rim or past the bottom edge of their armor.
So it's really an anti-personnel weapon for disciplined, repeated action in a crowd.
That's it. That completely shifts the perspective. It's a tool for penetration in highly structured warfare.
Okay, so let's jump across time and geography to something that almost feels like a time travel anomaly. The Viking Ulfberht sword.
This sword is genuinely bizarre from a metallurgical perspective.
How so?
The Ulfberht blades were made from crucible steel. This means the smiths somehow managed to achieve consistent, extremely high heating to purify the iron. And critically, these blades had a carbon content about 3 times higher than contemporary weapons.
Wait, they were achieving a material purity that rivals the industrial age.
Exactly. That level of quality wasn't consistently achievable in Europe again until, the 18th or 19th century. We're talking about unbelievably high-quality steel being forged between 800 and 1000 AD.
That's wild.
And the sources still debate exactly how they did it, how they maintained that extreme heat and protected the metal from impurities to get that consistency. It's one of history's great manufacturing mysteries.
Incredible. So let's synthesize the biggest visual difference we see across the globe. Curved versus straight blades. What does that choice tell us immediately about the combat environment it was made for?
The shape is really the signature of the system. Straight blades like the European longsword or the Chinese jian, they excel at versatility.
All right, the all-rounders.
They can slash and chop, sure, but their primary military strength is superior thrusting. And that is vital for targeting the gaps in armor.
And the curve, then, is for maximizing pure cutting power.
Precisely. A curved blade, like a scimitar or a dowel, converts the weapon's momentum into this really efficient slicing or sawing motion along a narrow contact point.
Perfect for cavalry.
Ideal for fast-moving targets, particularly in mounted combat where the rider's own speed adds all that kinetic energy. The Turkish kilaj even featured a flaring double-edged tip.
Which increased the weight right at the point of impact.
Yes, to maximize that slashing force.
Okay, before we move on, we have to mention the falchion. It seems to stand apart from these. It's designed for accessibility, not specialized artistry.
It's the practical workhorse of the medieval world. The falchion combined the raw chopping power and the weight distribution of an axe with the length and handling of a sword.
And crucially for military history.
It was vastly cheaper and simpler to manufacture than, say, a pattern-welded longsword. This made it an accessible, devastating weapon for mass-produced armies and common soldiers.
Okay, so moving from the geometry of the blade to the systems built around it. The German longsword system, documented by masters like Lichtenauer, it was incredibly philosophical. This feels more like kinetic chess than just a brawl.
That's a perfect way to put it. The core tenet was that the sword, or really your movement, has to control the opponent's blade, not just react to it. They developed this whole concept of master cuts.
The most famous being the Zornhau, the wrath cut.
Mhm.
What makes that specific cut so powerful?
It's an attack that anticipates and counters the defense at the same time. It's a committed diagonal strike, but if the opponent parries or tries to bind your blade, the strike instantly transitions into a thrust, the Zornhau or the wrath point. It ensures the attack is never fully wasted. You have to be thinking 2 steps ahead.
Okay, now here's where it gets really interesting and totally counterintuitive for me.
Yeah.
The technique for fighting fully armored opponents, half swording. We've all seen the images of knights gripping their own blades.
That is the aha
Yeah.
moment of longsword mastery. When you're facing a target encased in solid plate armor, the weapon fundamentally changes its purpose. The offhand grabs the blade, turning the sword into a short, stiff spear.
Which gives you the leverage you need to be accurate.
And forceful.
Yeah.
You can drive the point into those narrow gaps, the armpits, the visor slit, the joints. It turns a high-velocity cutting tool into a specialized anti-armor penetrating weapon.
And their training methodology, just for the fundamentals like footwork, was intense.
Footwork is the foundation of every single martial art. And the longsword system emphasized these intricate offline passing steps, triangle steps for repositioning. Our sources even highlight that advanced students actually train to execute cuts while airborne.
With both feet off the ground.
With both feet off the ground, specifically to build absolute balance and stability for attacks where momentum and weight transfer were just critical.
Let's contrast that heavy armored system with the later rapier revolution that swept out of Italy. They basically discarded 1,000 years of cutting tradition for pure point precision.
It was a complete paradigm shift. The Italian rapier masters like Capoferro and Giganti, they realized that combat efficiency really lay in simplification. The key insight was recognizing that combat happens along a single straight line between the 2 fencers.
Which, again, seems obvious now. But
Yeah.
the Spanish school at the time was still obsessed with these circular steps and complex, almost ceremonial patterns.
And by focusing on that straight line, the Italians perfected the lunge. This led directly to the modern fencing stance. Low center of gravity, flexed knees, weight on the back foot. All to maintain maximum reach while keeping your body and head safe.
And for defense.
They often use the complementary rapier and dagger system. You leverage the dagger in your offhand to catch the opponent's blade while the rapier keeps up that relentless offensive pressure.
Okay, finally, let's look east at the fluidity of the katana system.
Yeah.
The most iconic art there, the iaijutsu, where the draw itself is the attack.
Iaijutsu is the art of simultaneous drawing and cutting. It's 4 precise, fluid phases, all designed to deal with a sudden encounter. You have the nukatsuke, which is the swift drawing motion.
Draw.
Then the kiritsuke, the immediate cutting action. The chiburi, which is that crucial shake to remove blood and debris. And finally, the noto, the controlled and deliberate sheathing of the sword.
When you watch it done properly, it looks effortless, but it must demand incredible control.
Oh, absolutely. And unlike the rapier, the katana system fully integrated grappling once the distance closed.
Right.
When the fight devolved into close quarters, they entered what's called subazeriai. Samurai would use the crossguard, the tsuba, the pommel, even the sheath to deflect blows, or they'd use joint locks and throws, integrating jujitsu to create an advantage before finishing with the blade.
We've talked about the brutal demands of these fighting systems, the rotational stress of a keelage cut, the penetration force of half swording, the need for a katana to be lightning fast but also hold a razor edge. How did the actual material engineering meet those demands?
Well, the material science had to enable the martial system. It all starts with the foundation, high carbon steel, ideally around 0.8% to 1.3% carbon. That's what makes the iron hard enough to hold a sharp edge.
And it's interesting that smiths were very practical. They often repurposed scrap material.
They did.
I remember seeing that, using things like old vehicle leaf springs because they naturally contain the carbon and silicon additives needed to create that tensile strength.
That's practical metallurgy in action. Now, 2 really complex historical fabrication methods stand out. First, you have pattern welding, used in Viking and early Damascus steel. This is forge welding multiple billets of contrasting high and low carbon steel together.
So why all the hammering and folding? What's that actually doing?
It's about homogenization and structure. You're evening out the carbon content, removing impurities, and creating this internal layered structure which improves the overall toughness and helps prevent fractures.
And to do that, you need a crucial ingredient.
Flux. often in hydrosporax. It prevents oxidation and allows those distinct layers to fuse into a single cohesive piece of metal during the hammering.
And then we have the epitome of the art, the complex Japanese method of differential hardening for the katana. This seems to be the ultimate solution for balancing hardness and flexibility.
It really is the most sophisticated secret. It begins with Tama-Hagane steel, which they separate into high carbon for the edge, the Hagane, and low carbon for the core, the Kawagane. They laminate these together, but the crucial step is applying a clay mixture, the Tsuchioki.
And that clay is applied strategically, right, to control how quickly different parts of the blade cool down.
Precisely. It's applied thickly to the spine, but thinly or not at all to the edge. So when the blade is heated and plunged into the quench, the exposed edge cools instantly. It becomes extremely hard.
How hard are we talking?
Tool steel hard, maybe 60 on the Rockwell C scale, which is how we measure hardness. But the insulated spine cools slowly, so it remains flexible and tough enough to absorb the shock of an impact.
This raises a really important question. If a smith got the shaping perfect, but skipped that crucial heat treatment process, what would they actually have?
They'd have a decorative piece of metal. Without proper heat treatment, a sword is just a blade-shaped object, as our sources like to put it.
Wow.
The process is absolutely critical. First, you have quenching, that rapid cooling from cherry red heat around 1500 degrees Fahrenheit. That makes the steel hard, but also very brittle.
Which is why the second step, tempering, is non-negotiable.
Right. Tempering is reheating the blade to a much lower temperature, around 350 to 450 degrees. This relieves the internal stresses that got locked into the steel during the quench, and it restores the toughness and elasticity so the blade can actually bend without snapping. #outro.
So we've spanned continents and centuries here, looking at weapons designed for shield walls, mounted charges, duels, single quick draws. And yet, the sources seem to identify 4 unifying principles across all these disparate martial systems.
The fundamental rules of combat, they stay consistent regardless of the weapon. 1, footwork. It always forms the foundation of any effective technique. 2, blade positioning and distance controlling that gap between you and the opponent that determines outcomes. 3, timing and tempo are universally more valuable than just sheer physical strength.
I'm lost.
And 4, adaptation. The ability to change your technique based on the opponent or the environment, that's what separates the novice from the master.
So what does this all mean for the history of war? The sources made a fascinating note when comparing 2 Chinese weapons. Attaining basic competence with the straightforward, single-edged Chinese dao took roughly a week.
A week?
But mastering the elegant, complex, double-edged jian, well, that required up to a year of dedicated study.
Which leaves a really important question for you to consider. In the grand scope of military history, which approach ultimately proved more effective, the high art of a complex weapon system that required years of mastery, or the practical design that maximized battlefield effectiveness through rapid training and simple, devastating power.